Eric, and we will build upon what you already talked about with Eric. So let's focus a little bit more about force fields and some advances that are emerging in this field recently. So, as you saw, a force field is just a set of equation and a set of parameters that taken together, they are used to describe a system, molecular system. They can describe molecules, atoms, sorry, but in theory, they just describe spheres connected by springs or something like that. And so we can use a different level of parameterization for atoms or groups of atoms, for example. But we will focus only on atomistic simulation, so we will talk about atoms. And so all these parameters are once you define your set of equation, you have to fine-tune the set of parameters to describe a system, and usually to do so, you make some compromise and you try to optimize the parameters to reproduce some properties, and hence I can answer directly to the question about mixing force field. In principle, it's not impossible. It's very, very linked to what software you are using. For example, in Number, you can't because the problem is here. Okay, let's don't talk about we don't want to talk about building your own molecular dynamics engine, obviously. If you want to use what's already available, we can talk about LAMPS, GROMACS, Amber in the main ones. For Amber, for example, you are very limited in the set of equations that you can select. So, for example, I'm thinking about the Dreidig force field. You can't use it in Amber because there isn't a piece of equation that is needed for such force field, for example. But for example, in GROMACS or in LAMPS, you are able to choose from a good plethora of different functional forms. And so in theory, you can mix and match force field practically, but you're not guaranteed or the results. Mainly, all of this is GIGO, garbage in, garbage out. If you don't have good input parameters, you will end up with bad output results. And so if the force field were not parameterized to work together, you will not obtain reasonable results. This is particularly true and is particularly useful for example, in LAMPS, because in LAMPS you can here we are talking about simple force fields for atomistic simulations of let's say organic molecules. In LAMPS, you can have a particular force field for metallic atoms, and so metals in general, they don't behave like organic molecules with single, double, and triple bonds, etc. And so there are a completely different family of force field that is used for simulating metals. And in theory, in LAMPS, you can mix and match and so parameterize some part of your system with these metal force fields, some part of the system with the standard Lennard-Jones force fields, the one that we're talking about now, and then take some parameters some function that mix the two. But you have to check if everything is correct, let's say. So in theory you can, but it's a lot of work, let's say. So going through more in detail now with the Amber force field, this is the set of equation which was selected for the Amber force field. And here I highlighted all the parameters that you have to fine tune when you are describing a new molecule, a new atom. And what you're doing usually with these standard families of force field is you have to firstly type your molecule. In typing your molecule, you are assigned to each atom a label which correctly represent the atom type inside of the force field. Here I reported the atom types present in the GAF force field, which is the general Amber force field, the force field in Amber that you use to parameterize all the small ligands, for example, or what is not protein, lipid, or DNA, for example. These atom types come with some description that help you identify which label to add to each atom. Obviously, also there are some tools. Amber is very, very good in that because it has many different tools that are able to automatically assign these atom types, but you should check them after the automatic parameterization. Once you have added the atom type, but once you have typed your molecule, uh, what a force field is just a text file in which the computer program, or you by hand if you want, you need to collect all the parameters needed for the equations from the atom type. So if I have a carbon Ca and a Ca, I have to get the parameters for the bond between Ca and Ca, etc., etc., etc. So a force field then is just a combination of atom types, groups of atom types, and their parameters for bond angle and dihedral parameters. And one problem of such method is that if you want to insert a new dihedral, for example, and this is particularly true for dihedral because usually angle and bonds are easily transferable between different molecules, let's say. While a dihedral angle, what is a dihedral angle? The dihedral angle is the rotating, the potential around the rotation of a single bond, which is rotable. And this rotation is particularly influenced by the chemical environment around this bond. And as you can see here, the description of the atom types, they somewhat describe some chemical environment, but they don't describe a methyl group attached to a single bond or a phenyl group attached to a single bond. And these two groups obviously have different creates different, let's say, dihedral potential around such a rotable bond. So usually what you want to refine, particularly this is true for polymers, is the refinement of the dihedral angles. If you want to define a dihedral angle, you have to redefine a new atom type, pretty describe in detail with what how to assign such atom type, and then you have to define the new properties, new parameters for the dihedral, and then also all the other possible interaction of such atom type with all other chemically relevant atom types. And this is tedious and prone to error, obviously. As you can see here, this is an example from the literature in which the authors wanted to reparameterize the GAF force field, which is the force field of amber for general molecules, for fluorinated alkanes. As you can see here, fluorine has just one single atom type in amber. So every fluorine is identical for amber, and this is obviously not true here. As you can see, the dihedral parameters, standard dihedral parameters for fluorine were very, very far away from the actual potential derived from quantum mechanical calculations. And also, when they use molecular they tried to obtain the minimized structure of this molecule over here. They obtain this very straight molecule, which is very, very different from the same molecule obtained at the quantum level of calculations. While when they were able to optimize all these dihedral parameters, they obtain such configuration with optimized parameters, which is very, very nicely similar to the one obtained at the quantum level. And it is also reflected on a very, very different configuration in the bulk of such molecules. So you can see here they are packing very, very well. Here they are dispersed in a very different way, let's say. And so the fine-tuning of the dihedral can be pretty important. What can we do is in theory, we can use a new approach in force field development, which is exemplified by the OpenFF initiative, in OpenFF toolkit, OpenFF force field. And this force field allow you to forget about atom types. You just use direct chemical perception. What does it mean? They devised an encoding specification called Smirnov, which is based on smarts and smirks. These two strings rules are on the same family of smiles, which maybe you have already heard of. And they are able to describe, smarts are able to describe a pattern in a molecule, so is used for substructure query. And smirks is able to describe transformation, chemical reaction, but for us, the important thing of smirks is the ability to tag atoms. What I mean is, with a triple example, here is the Smirnov encoding for a carbon atom, so atom number 6, with the 4 substituents, so a sp3 carbon, which is bound with a single bond with an atom type, atom number 8, so an oxygen atom. These match any CO other, bond, single bond. And here you have the tag 1 and 2 to identify that the bond parameters have to be added to this bond over here. This is obviously trivial because we have only this atom, sorry, only this bond, but if you want to give more chemical context, we can use this string, which is the same carbon atom, sp3, bound to at least one hydrogen atom, which then the carbon atom is also bound to the oxygen, and with this oxygen is also bound to another carbon atom. So here we are describing some ester, and here we need the tags because we have different bonds, and the tags are able to define to which bond, the CO bond, the bonded parameter are to be added. So this is the overall Smirnov encoding. And in the OpenFF force field, the OpenFF force field is distributed as an XML file. So it's a standard file format, which is easily human and machine readable, which is a nice thing. And you can add many different tags in this XML file. And so in this file, you have everything explicit. And if you start work with these things, this is a very nice thing because usually, for example, in Amber, the potentials are not reported in the force field files. So you know it from the literature, from the manual, but when you open a force field file, you don't understand everything from sight. While here you have everything explicit. You have the potential, you have the units, which also in Amber are not explicit, and also I think in Gromax are not explicit. You need to know them you need to know your software, but here is everything present in the force field easily. And this is also very, very important because the toolkit itself can convert between units because the toolkit is unit aware, and so it can then convert everything and output a parameterized molecule for many different atomistic force machinery. For example, a classical example, Amber uses kilocal per mole and Armstrong Gromax uses nanometers and kilojoule per mole. So a big difference. You can transfer the number as they are. And also another thing that is very important is very nice. We have in the Lennard-Jones parameter, we have to define a distance, and the distance can be defined in different machineries with this value over here, the sigma value or the R mean value. And you need to know what you are defining, and you need to know what is reported in the literature, and it's a common source of error, is the mix and match of the two. Here you explicitly say what you are writing, and the force field, the toolkit that will then convert it for you. So it's very, very nice. The toolkit also includes a bespoke fit, which is an automated solution to create custom-made parameters. What does this mean? Bespoke fit will run some quantum level calculations with open source softwares, and will automatically refine the ideal parameters for your molecule in an automatic way, let's say. It will take some time. By time I mean hours to days, but it will produce you a force field that is tailored to your molecule. So we have some practical example. We used this OpenFF force field in comparison with OPLSA, which is a standard all-atom force field, general all-atom force field, on some thermoplastic polyurethanes which were made from HDI and different molecular weights of PEG units, so PEG segments, sorry. And this work was done also with Tatiana. And here we use the OpenFF with bespoke fit and OPLSA and OPLS. And as you can see from the structural properties were were correctly predicted by both force fields, while we also partnered with some experimentalists which gave to us the glass transition temperature of such polymers and their elastic modulus. And as you can see for the TG, both force fields were able to retrieve to predict the correct let's say behavior, the decrease of the TG with elongating the PEG units, PEG chain length, but they both are far away from the experimental values. We can say that OpenFF is getting closer to the experimental values, but this is a known fact for the estimation of glass transition temperature. what was interesting was that experimentally you observed this bell shape in the behavior of the elastic modulus, for which we have a decreasing and then a re-increase of the elastic modulus predicted with the elongation of the segment of the TPU. And the same bell shape was reproduced at different molecular weights, but this is not very important. We can fine tune it more with the OpenFF, while it's completely absent in OPLS simulations. In another project in which we are involved with other computational groups in Italy, we had a partner which had the role to rebuild from scratch a new force field just for PT and PF, which are two important polymers for packaging, for example. And this group was able to recreate from scratch a new force field for fine-tuned only for PT and PF. So they design the atom types just for these molecules, all the dieder, all the angle, all the bonds, all the energous interactions, all the non-bonding interactions, very, very fine-tuned. With this force field, we performed some atomistic dynamic calculations. The first ones were very, very nice because we observed that with the QM-derived force field, was able to very better reproduce the experimental literature range of density, and particularly also of glass transition temperature for PET. We can see here in red the experimental value, and we see that with the QM-derived force field, we are getting very close to the experimental value. This was nice, but in this project, we also wanted to explore the full molecular multiscale simulation ladder, let's say. So we are here, and they derive the force field here, they pass the information to us here, and now we wanted to pass some information to the continuum models to get some practical properties linked to geometry and the shape of the packages that are used then by the industry. And one such information was the diffusion constant in such polymers of small molecules. We wanted to start with the small molecules like oxygen and water molecules because they are responsible for degradation reaction inside of the packages usually. So we derived such a property, and the results were not so good because we weren't able to improve much from the OPLS force field, and in some cases we also were able to get very, very bad results compared to experimental values. So the results were not very good, but this was somewhat expected and is linked to the fact that I told you before that you have to be aware of how was your force field parameterized and how to what properties, what was the end goal of the force field. Because, for example, here we reparameterize from scratch everything for PT and PEF, our partners. But usually, when you parameterize something, a new force field, or in general, the general force field, when you have to define the parameters for the Lennard-Jones interaction, so the non-bonding interaction, which are not related to the partial charges of the atoms, this interaction, usually you set the parameters for the self-type, same-type interactions. And then you use combination rules to derive the parameters for the cross terms with other atom types. And usually then use these, there are different sets of these combination rules. These are the more common, which are just fancy names for the arithmetic mean or geometric mean of the two parameters. What was the problem here is that in the training set that they used to parameterize the force field for PT and PF was only PT and PF molecules. So we didn't have our force field, we never saw oxygen or water. So the force field was very, very good in reproducing properties linked only to the polymer, but once you introduce something else, the magic is broken, and the force field is not anymore an improvement compared to OPLS. So you should reparameterize probably Lennard-Jones interaction between the fine-tune the Lennard-Jones interaction here between oxygen and water molecules and the atom types defined for the PET molecule, for example. So this closes the chapter, I wanted to say about force fields. And I wanted, in the second part of my talk, I want to talk about enhanced sampling, so MD on steroids. So what we can see with MD, which is apart from what we can see from just moving the atoms and see what happens. Because when you talk about what also you saw with Eric, usually when talking about a standard microdynamic simulation, you are over here in the multi-scale approach. You have you can describe the system in the range, the length about nanometers, tens, hundreds of nanometers, and you can simulate stuff for that, sorry, phenomena that happen in about in the time range of microseconds, let's say nowadays. It's true that we had a big improvement, as Eric said, from 10 days ago, 10 years ago, and now the speed of the simulation were skyrocketed. We will see probably something like this with the advent of quantum computing in the near or far future, maybe, but with the actual now with the scaling we have nowadays, probably we will not see any more improvement in this kind of situation, simply because the MD algorithm itself is not trivially parallelizable, and so the big improvement was from the use of CPUs to the use of GPUs, which is in reality is a parallelization, but it's limited, let's say. And so nowadays you can't just simply run bigger simulation or longer simulation on higher bigger HPC systems, because all codes will not scale up very well over lots of GPUs, for example. So what you can do is use, so you're limiting such in the realm of microseconds of simulations, but many rare events, which are the most interesting things that you can observe, usually need some seconds or hours of time of simulation. I'm talking about protein dynamics in general, protein folding, but also moving part of the proteins, phase transitions in material science, for example. These phenomena need some form of enhanced sampling to be studied by molecular dynamics simulations. And why is so with a very overall picture? You can think about your system, your microdynamic simulation box system, which is moving in a very big hyperdimensional space, the configurational space, which is 3n dimensional with the n number of atoms, because we have, in principle, there can be some restraint, but in principle, you can have 3 degrees of freedom for each atom. So this space of possibility is very huge, is very highly dimensional. So let's shrink it down to a 2 dimension space in which we have just collapsed all the dimension to just 2. And for each configuration of your system, you can define a free energy value. And obviously, your system it like to stay at lower values of free energy usually. And so when you start your simulation from whatever in this configurational space, you usually end up in the nearest free energy minimum, and then you'll stay there practically, because to escape from a free energy minimum, you need to escape a free energy barrier, and the probability of escaping is linked to the energy that you have, the height of this barrier, and the temperature of the energy that you have. And so usually you just start in a minimum and stay in that minimum for all the simulation time. Usually the barrier that you can easily overcome are very low, because it's linked to KBT, and at standard temperature, just 10 kBT, so 6 kilocal per mole, have a very low probability crossing. So what you can do is you can act on temperature, but if you just increase the temperature, this probability will go straight to 1, but this goes for every energy barrier. So what's happening when you increase the temperature, just increase the temperature, is just that you are flattening out all these free energy landscape. So you're flattening out, okay, you are exploring more, but you're exploring something which is not related to what you wanted to describe in the first place, because usually you want to describe the free energy landscape, the accessible states of your system at room temperature or similar to room temperatures. So just giving a temperature is not enough, but you can still rely on a computational technique which is called temperature rapid exchange. You can then improve this algorithm to go to run with other things, not just temperature, but let's talk about temperature. So we are talking about a technique in which you start many different simulations, completely unrelated for now. So they can run on different server, on different places on Earth. It's not a problem. So this part is very, very easily parallelizable. But at some interval, sorry, each of these simulation is at a different temperature, increasing temperature, obviously, from the first one, which is the one you're interested in, and then you increase the temperature in the other simulations. And at some defined time intervals, you try to exchange configuration between two nearby temperatures. What does this mean? You at this point you ask yourself, the simulation asks itself, is the configuration here at this high temperature probable, possible, plausible, it's acceptable at a lower temperature? If no, each simulation continue in its temperature, its configuration continue in its temperature, otherwise they are exchanged. By doing this trick and then just analyzing the lower the room temperature, let's say, simulation, you get a simulation which is not continuous in time, obviously, because you have configuration that are popping in from different routes, let's say. But this is the interesting thing, because here you are exploring states which are stable, reasonable, which are plausible, which are okay at room temperature, but coming from probably from different region of the phase space, because here we have of the configurational space, because, for example, here we have the blue trajectory, blue configuration, which started at high temperature. So once this configuration reaches here, is able to explore more freely the configurational landscape, then it's cooling down here. And so probably here, this configuration is at a different minimum than the one that started here or the one that is over here. And so you are exploring more of your free energy landscape without having to, without distracting it. And this is very, very nice, but also is very, very limited, because here we are just exploring more, but you can't in this kind of setup drive your simulation toward to explore, some particular states you are interested in. So what you can do is, what you usually do is to rely on some enhanced simulation techniques, which is based on enhanced sampling. On collective variables. What is a collective variable? As we told before, the space on which these configurations are moving is very, very big. The configuration space is at least in the range of 3n dimensions. It's a little bit more less because you can have some degree of some restraint, but it's very big. So you perform some sort of dimensionality reduction, and so you can also use which is linked PCA, but we are not using. Usually, we are not talking about PCA. Here, we are talking about definition. So you human define a collective variable, which is a function of the same coordinates of the system, and so you reduce the free energy landscape on just you project all the free energy landscape on just this collective variable. You can add how many collective variables you want, up to 2. You can easily visualize the free energy landscape, because with one collective variable you have something like this, and with 2 collective variables you have something like this. With more than 2, you can easily visualize it, because to add the free energy, you will end up with 4 dimensions. So we have some problem of visualizing it. But so let's talk a little bit about what are these collective variables. These collective variables have 2 main scope, the main functions. The first is that they make the system more understandable to the human. You can study it, and the clear example of such collective variables is, for example, for a drug binding. You have a protein and a drug, and the drug act on the protein by binding, so by entering some cavities and staying there and modifying the action, the activity of the protein. So usually for a drug, you can define two defined states: the drug in the solvent, which is inactive, and the drug bound to the protein, which is active. And so if you define as a possible corrective variable the distance between the center of mass of the drug and the center of mass of its binding pocket, here you have a good collective variable for you to understand that here we have sorry, I don't know if you see I can stop it, maybe no, okay. In here you have the minimum, imagine this is this distance we already talked about. This at low distance, you have a minimum, which is the drug bound to the protein, and at higher distances, we have another minimum, which is the drug unbound, the drug free in the solvent. The difference between these two states, the energy difference is delta G of binding, let's say, of the protein of the drug, and this is the transition barrier from both sides. So this collective variable is very nice, very useful to understand the system. Is also so this is able to accomplish this function, but you will also use collective variable to drive in some way your system, to push your system, to move your system, and so a collective variable must discriminate, must show you clearly the metastable states that you're interested in this case, bound and unbound, and this collective variable is more or less okay for this. But you can also use this collective variable to push your system. Let's imagine you are starting with a drug unbound, and you, in some way, with some technique, you force your system to decrease such distance, okay? And so you are forcing the drug to enter its binding pocket. This is doable up until a point. The drug will follow your push direction and will approach the protein. Once the drug reaches the surface of the protein, there is a problem because you're only trying to push the drug, but the drug usually have to also reorient itself to find the cavity and enter into its binding site. Or, and this is worse, the protein have to change its arrangement to accommodate the entrance of the drug. And if you're just pushing this collective variable, you have a suboptimal collective variable because you are pushing, but you are missing some other slow degree of freedom of your system. In this case, the rearrangement of the protein or the rearrangement of the drug. And so you can push whatever you want, but you have to still wait for the mini barriers that are not allowing the drug to orient itself, or the higher barrier that usually exists for the protein to move, to accommodate the drug inside the binding site. And so this is a suboptimal collective variable, the distance. There is another problem with this collective variable, which is that this collective variable is also degenerate in reality, because what does it mean? Degenerate is a collective variable that map different physical states to the same collective variable value. In the example before, I told you that at high distances, the drug is unbound. This is not really true because, okay, at very, 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 very high distances, yes. But at intermediate distances, we can have the drug unbound, and this is the binding site. You can have the drug unbound, but we can have the same drug into another pocket, blocked inside another pocket of the protein, or we can have the drug adsorbed on another on the surface of the protein. So these states are clearly not the same, and they should map on different regions in the free energy landscape. But for your collective variable, which is just the distance, they are the same identical state. And this is obviously a bad thing, both for the use of the collective variable to push your system, but also for your interpretation of the results. So what you would do usually, okay, you try to define the best collective variable as possible, which is not degenerate and not suboptimal, but usually this is very, very hard. You have to add some collective variable. You can add in principle the whatever number of collective variable you want, but there are some problems. The first problem is the human interpretability of the results, because it's hard to interpret anything that has more than two collective variable. You can just see things in 3D. But particularly also the different method that you can use to drive your simulations and to explore the free energy landscape, they almost all struggle when you go over the three collective variable, let's say. With Opus, you can try to go a little beyond that, but usually you have to stay in the low, as few number, as few, you usually need to use as few collective variables as possible. So for them to complete our example of a drag unbinding, which has to reorient itself to enter the binding pocket, you will use the distance. It's fine. It's the easiest to interpret, but you should add at least another collective variable, which is this is the needed because the number of ligand protein contacts or the number of ligand water contacts is the same. It has the same. It has the same results ultimately, because it's used to discriminate. This is needed to discriminate the degenerate problems. So you have to define easily identify, is the drug really unbound or is still somewhere near the protein? So this is very important. And then this is needed for a correct interpretation of the result, while also you can add this other corrective variable to speed up the calculation, because in this way, we adding theta is representative of some orientational angle of the drug. And this theta angle is able to push and to discriminate between the suboptimal, productive or non-productive poses once the drug is near the binding pocket. And so this is what I wanted to say about collective variable. Let's imagine you have defined your set of collective variable in a good way. And now let's forget about the other collective variable and just focus on one, because it's easier to represent it and to move it and to show what I'm meaning. But all this stuff is then done in also in two or three collective variable space. So here you have an unbiased simulation on the CV space. Let's say here I have I put it a random number. So let's say a random range. Let's say that this is the distance between the drug. So here is around 0 and here is around 2 nanometers, 3 nanometers, I don't know. Okay. If you start with the drug bound into your binding pocket, and as I told you, you just can't, if this barrier is high enough, you will not see an escape of the drug and an exploration of this region of minimum. And another thing is that if you collect all the histogram of the visit count of how many times you visit each collective variable, in theory, you should get here a shape that is the negative, let's say, of this true potential in theory. But you don't have enough energy here, so you're just sampling this energy minimum. What you can do, you can use, for example, umbrella sampling. Umbrella sampling is a technique in which you define your collective variable. You don't know, obviously, this true potential. This is the end goal. You want to retrieve this potential, this shape. So you take your collective variable, you subdivide it in some number of windows. It depends, can be 10, 15, 50, 60, it depends. And then at each window, you run a single simulation with an umbrella potential, a U-shaped potential, which restrain the system at such position in the CV space. Here I will show you this simulation in sequence, but you have to know that all these simulations are completely independent, and so they can be run on different server on Earth, not a problem. You have just to collect these histograms, and these histograms have to overlap nicely. Here they are no overlapping, not so much, but it was nice for the representation. You should have more overlap between the histograms. Once you collect such histograms, you are able to use WAM or other statistical analysis techniques to remove the effect of the umbrella potentials and retrieve the true potential. So each system in each windows is moving, on top of the true potential, obviously, because you can't touch it. It's always present. And so by removing the umbrella potentials in a meaningful way, you are able to retrieve the true potential. This is a very nice technique because it's trivially parallelized. You can easily run it in parallel, because you are not restricted in the number of simulation you can run if you have enough GPUs. But it is a technique that struggle when you want to add more than one CV. you can, in theory, use 2D WAM, but is the number of simulation that you have to perform explodes in number, and also it can be pretty tedious to converge. So you can use, but it's very, very nice, very, very simple to apply for for problems where a single CV is enough. Um, Otherwise, you can use other techniques, one of which is metadynamics. And in metadynamics, you run the simulation freely, and the end goal is to obtain to create a metadynamic bias that is a time-dependent bias, which is built by the method during the simulation. And ultimately, the metadynamic bias will be the negative of the true potential, let's say. And this bias is built by, at some time interval, the simulation drops a repulsive Gaussian to the actual potential collective variable value in that time. And in this way, you build this metadynamic bias as the sum of such Gaussians. And the easiest thing to imagine this is the blind guy with an infinite pocket, which walks around in a pool, and at some interval will, with its hand, will drop a handful of sand. Ultimately, it will escape the pool because it will fill the pool. And this is the same concept here. You are filling the pool with these biases, and ultimately you are escaping and filling the other pool. And then the end goal would be to create a flat potential in which the system is able to explore both all the CP space freely, let's say. This is nice, but as you can see with the standard metadynamic, you easily overfill, you easily put too much potential. So the real method that is used nowadays is well-tempered metadynamics. The main difference is just that the height of the Gaussian is adjusted based on how much potential was already dropped in a place. So here we start with this height because we have no potential. If I move the simulation on, sorry, to another place, here we have already dropped potential, so the yield height is dropped below, is almost halved. Then if I go over here, I don't have dropped any potential for now, so the yield height is again high, and so in this way you will get finally a nice and smooth filling of the true potential biasins. And you will end up, you will see here a very nice representation of the histograms will match the true potential easily. And there is another similar implementation nowadays, which is the gold standard nowadays. Instead of metadynamics, if you need to try to learn something of this pool of techniques, I would suggest you to learn to use OPES, which is very, 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 very similar from the practical actual point of view for the user. The theory behind is a little bit different because you're not dropping Gaussian, and you are not constructing the metadynamic bias by summing this Gaussian, but you are estimating the overall bias at every time step. The main difference you can see here is that I'm here, but I'm still updating all the bias. So the bias is changing. From the practical point of view, this method should converge more quickly, and it has many less parameters that have to be optimized compared to well-tempered metadynamic when you run this method. So ultimately, all this method will produce for you this kind of images in which you have your free landscape in 2 dimensions and then the project on one of the 2 dimensions. And usually you see such kind of these 3 plots in papers and not these ones because they are harder to interpret. This is the easiest one to interpret. So I think I'm running out of time, so I will just give you some quick example of what you can do with these enhanced sampling techniques that is not related to the building of such shapes. And for example, in drug design, we are usually focused on the development of the determination of delta G of binding, so the capacity of a drug of strongly bind to the protein. But in recent time, it emerges that it's very important also the residence time of a drug. So how much a drug stays bound to the protein. This is true both for the target protein because the drug must act for a reasonable amount of time, so usually seconds, hour, minutes, days. But also it's important for molecules that carry around the drug. For example, human serum albumin. Here we want a reasonable delta G of binding, and we want a reasonable residence time in the range of seconds, usually, because you don't want your drug to be stuck to the albumin and then don't act on the real target. So we can use random sampling to obtain such residence time. Residence time, obviously, you can't obtain with unbiased simulation because the unbiased simulation would take you should simulate seconds, minutes, hours. It's practically impossible. But the probability of escaping from the drug bound is related to the height of the barrier, and the height of this barrier can be lowered by adding some potential, for example, with metadynamic, and this is true also for OPES. So what you have to do is just add some bias to make easier the escape. One important thing is that you must not add bias on the transition state. You should not that you should preserve the transition state dynamics. So you must not add biases here. So there are some techniques that allow you to decrease the bias deposition or the bias update for OPES in a way that you fill the bias and then wait for the drug to escape unbiased, let's say. Once you get the biased resident time, so once the simulation escapes and you stop it, you see it escapes and you stop it and you get the time of the simulation, so imagine some nanoseconds. And then you have to get the true unbiased time, and this is done through the calculation of an acceleration factor, which is function of the biased potential that was added by the metadynamics or OPES method. So once you have your alpha and your biased tau, you can get your unbiased tau. Obviously, with these unbiased tau, from one simulation, you get just one value, and we don't rely on just one value, particularly for this kind of stuff, which is very, very, you have lots of variability here. You don't have a nicely small Gaussian of results. And so usually what is done is you perform many of these simulation, at least 15 at minimum. And then you build the cumulative distribution function, which is the probability that a drug is escaped at some time. So here we have 0, a little bit more than 0, and then we have 1. And then such phenomena can be modeled with this theoretical curve. And so you can fit the theoretical curve. With the fitting, you can get you get two good results. One is the actual tau, the actual resident time, and also you can perform some statistical analysis and see if your data is well fitted to such curve. And we apply these to
Dominic, sorry, 5 minutes. You have 5 minutes.
Okay, great. So here I wanted just to show you that we applied this method to drugs that bind to albumin, and we saw that the residence time estimated by simulation and experimental residence time obtained by KNETC we were in the same good agreement, and they also agree with they are also relevant. Sorry. A good estimate for a drug that should be carried around by human serum albumin, but not sequestrated by human serum albumin. I had also here an example of a more standard use of OPES metadynamic, but I think I can also skip it because in a way that we have some time for the question if you want, because I think we are. So thank you for your attention.
Thank you very much. Thank you very much. Very interesting for me. It was a lot of new things, how the traditional molecular dynamics is advancing. So many new directions of advancing and improving. So we open the questions session, please.
Thank you, Domenico. Thank you very much for your lecture. Very interesting and very clear. And it's just for me, I would like to understand what could be the algorithm as if I want to develop some force field parameters which are not available yet in any force field. So we need to understand that we can use some experimental results, some quantum chemical calculations, but in general, what do you recommend?
Sorry, I get that you are talking about the development of force field, but I don't hear you very well, so I didn't understand.
I mean, the atomistic force field, something like OBLS or maybe open force field, but you don't have parameters in this force field, don't have available these parameters. How to develop open parameters?
Okay. So the question is how to develop new parameters for an existing force field.
Yes. For compound which is not already implemented, for some bond which is not implemented to the.
Okay. So the first thing that I would do is to start from some quantum chemical description, from quantum chemical calculation of the bond or angle and the integral that involves the new atom types. Let's say, let's talk about atom types because it's easier, but this is also true for the OpenFF model in which you don't define atom types, but you still have to identify to which bond you want to add the parameters. So you have the first thing to do is clearly to start from quantum level calculation is possible because as you can see here, you have maybe I can zoom a little bit. Here you have you can perform what is in this case called a dihedral scan, in which you check the relative free energy change in the dihedral angle in this case, but you can also do it with a bond or an angle. And then you usually if you are adding on a already developed force field, you stick with the equation of such force field because it's easier. And so you simply have to fit you set the equation, you just have to perform some kind of least square fit to the actual quantum chemical potential with the equation, with the force field equation, and try to reproduce the potential with and you derive the constants. Then ideally you should also run your actual atomistic simulation, plot the probability. So these free energies can be also computed by the probabilities that you by collecting all the same values of the angle during an atomistic simulation, and you try to match also these possibly because with quantum calculation and by fitting here you are just fitting the precise value of this bond alone, but there can be interaction between the different bonded parameters in the force field. So usually it's also nice to have a check with the actual molecule you have with atomistic force field, with complete atomistic force field you're using. Then also you can try to match with some experimental data if available. Obviously, this would be the holy grail, but it's usually they're not available. So
okay, thank you.
Thank you very much. Some more questions?